Here is a combined summary of the 2 pages. This study conducts a comprehensive comparison of semi-supervised learning methods for anomaly detection in hydraulic condition monitoring systems. The authors highlight the significance of condition-based maintenance in hydraulic systems, where anomaly detection remains challenging due to scarce and tedious labeling of anomalous data. To address this, semi-supervised learning methods are employed, which utilize unsupervised learning as a feature extraction mechanism to aid supervised learning with limited labeled data. The authors provide a thorough data analysis and feature engineering of an open-sourced hydraulic condition monitoring dataset. Various semi-supervised machine learning algorithms are implemented and evaluated, including traditional standalone models, e.g., one-class SVM, robust covariance, ensemble models, e.g., isolation forest, and deep neural network-based models, e.g., autoencoder, Hierarchical Extreme Learning Machine, HELM. The customized HELM model is found to outperform other semi-supervised algorithms, achieving the highest accuracy, 99.5%, lowest false positive rate, 0.015, and best F1 score, 0.985. The study emphasizes the importance of semi-supervised learning in situations where labeled data is scarce, and the system is complex with many potential anomaly types. The dataset used in this study consists of sensor data from a publicly available hydraulic system, with 2205 samples collected over 2,205 minutes. The sensors used include pressure, temperature, and flow rate sensors, as well as virtual sensors representing computed values. The condition variables describe the health status of critical components in the hydraulic system. The study's contributions include a systematic comparison of semi-supervised learning methods for anomaly detection in hydraulic systems, and the development of a customized HELM model that achieves state-of-the-art performance. The results highlight the potential of semi-supervised learning in addressing the challenges of anomaly detection in complex systems with limited labeled data. The research paper discusses a hydraulic system condition monitoring dataset, focusing on anomaly detection in terms of internal pump leakage. It presents a comprehensive analysis of sensor data, featuring engineering to reduce dimensionality and enhance model effectiveness. The dataset includes a large number of attributes, necessitating feature engineering to transform time series sensor values into meaningful statistics. The study employs various semi-supervised machine learning algorithms, including robust covariance, local outlier factor, and one-class SVM as standalone models, and also explores ensemble learning with isolation forest and deep learning with autoencoders for anomaly detection. The approach involves computing series-oriented statistics and transforms for each sensor, replacing the original attributes with mean, variance, skewness, and kurtosis. This procedure yields instances with 68 attributes, which are then used for training anomaly detection models. The paper highlights the importance of dimensionality reduction and feature engineering in handling large datasets effectively, ultimately aiming to improve the accuracy of leakage status prediction in hydraulic systems. The research paper discusses the application of Hierarchical Extreme Learning Machine, HELM, for anomaly detection in data. HELM is a semi-supervised learning method that stacks multiple layers of extreme learning machines, ELMs, to create a deeper structure. This approach allows for the capture of critical features representing the input data. The process involves training the ELMs using normal data samples, followed by the transfer of captured features to a one-class classifier for threshold fine-tuning. The framework is illustrated in Fig. 5. Evaluation metrics such as accuracy, precision, recall, and false positive rate are used to assess the performance of the model. The results, as shown in Table 3, demonstrate that HELM outperforms other semi-supervised methods, achieving the highest accuracy, 99.5%, lowest false positive rate, 0.015, and best F1 score, 0.985. The confusion matrix visualizations in Fig. 6 provide insight into the correctly classified number of normal and anomaly instances. Additionally, Fig. 7 and Fig. 8 visualize the distribution of 1-y-test, THRD for the HELM method, further supporting its effectiveness. The research paper examines the application of semi-supervised learning methods for anomaly detection in hydraulic systems. It focuses on the effectiveness of the HELM method, which demonstrates state-of-the-art performance in accuracy, false positive rate, and F1 score. The paper also highlights the limitations of the current approach, specifically its inability to detect the type of anomalies. This is evident from the visualization of the indicator, which shows similar distributions for weak and severe leakage samples. The study emphasizes the need for further exploration into semi-supervised methods that can detect the potential fault types. The paper provides a comprehensive review of existing studies and methodologies, including machine learning approaches, deep learning techniques, and ensemble learning methods for anomaly detection in IoT and industrial control systems. It concludes by emphasizing the importance of condition monitoring for hydraulic systems and the potential of semi-supervised learning for improving anomaly detection capabilities.